So this video is about k nearest neighbors, and I will be discussing both the case of regression and multi-class classification problems. So first, let us start with regression. Let's say you have a two-dimensional input space. So we have two inputs, x1 and x2, and then you have a bunch of data points. Let's take 4 as an example. Okay, so we have 4 data points, x1, y1, and so on. And then in addition to these training points, we are given this red dot, this red point here. So at this red point, we don't know the label, we just know the input features. So we know x, and we would like to approximate the label y. So what the k nearest algorithm does is that it says the ground truth label at this red point would be very similar to the ground truth labels of the k nearest neighbors. So what does this mean? Okay, so let's say k was equal to 2. So when k was equal to 2, if k is equal to 2, then the two nearest neighbors would be these two. Okay, and as per the k nearest neighbor approximation, the ground truth label at x would be approximated by f of x, and this would be nothing but the average of these two ground truth labels. So let's call this x1 y1, and then the other one is x2 y2. So the ground truth label at x would just be an average of these two. This is the case for regression. Okay, and we will discuss the case for classification later on. What happens when k is equal to 3? So when k is equal to 3, for this particular case, this point would be the third nearest neighbor. So the neighborhood now would change to this constellation of points. Okay, and then the approximation would read y1 plus y2 plus y3, assuming this is y3 by 3, and so on. And if k is equal to 4, then the constellation would change to this set. Okay, so all the points would be included in that case. Okay, so that's the basic idea of k nearest neighbors. But then the question is, how do you identify these nearest neighbors, or how do you actually define the neighborhood of a point, right? So because we need this definition of neighborhood, only then can we identify these 2 points, let's say when k was equal to 2, or these 3 points when k was equal to 3. So we really need to understand how to define the neighborhood, and this is what I will discuss next. Now, to define the neighborhood, we need something called the distance function. So this distance function is usually denoted by d, and this takes as input 2 points. Let's call them xi and xj, and this returns to you the distance between these 2 points. Okay, so once you have this distance function, finding the k nearest neighbor is straightforward. So if you have 3 points and then you want to find the 2 nearest neighbor of this new point shown here with a cross, you just compute the distance between this cross and these 3 points, and then you pick the 2 points which are the closest to x. In this case, it will be these 2 points. So when it comes to defining the distance function, we have a lot of flexibility, and we only need to make sure that 3 properties are satisfied. Okay, so the first one is that the distance between x and x should be 0, obviously. And the second property is distance between x1 and x2 should be greater than 0 for all x1 not equal to x2. So if you have 2 points which are not the same, then if you measure the distance between these 2 points, then it should be greater than 0. Right? That's how you should be defining your distance function d. And then the last one is something that's called triangles inequality, and it is best explained with the help of a triangle. So if you have 3 points x, y, and z, then triangles inequality says that going directly from x to z, when you go directly from x to z, you will be covering less distance as compared to when you take a detour and visit y as an intermediate stop. This means distance between x and z would just be less than the distance between x and y plus distance between y and z. So the property is very intuitive. So if you define a function d that satisfies these three properties, you're good to go, right? So that function would be a distance function between xi and xj. And as I said before, once you have the distance function, getting the k nearest neighbors is straightforward. But let's just formalize it better. So this is how the k nearest neighbors algorithm would work in practice. What you would have is a bunch of n data points, and then you would like to make a prediction for some new point x, right? So what you would do is, since you have a distance function, you would first compute these n pairs, x1x, x2x, and so on up till xnx, right? So once you have these distances, you would sort them, and let's say, for example, that x2 has the smallest distance, so we are sorting them in the ascending order, and then we might have x3 which has the second smallest distance, then we might have x4, and in the end we might have x1, which has the maximum distance relative to x. And if your k was equal to 2, then your nearest neighbors would be x2 and x3. So the approximation for the ground truth label at x would be y2 plus y3 by 2. Likewise, if k is equal to 3, then you would take x2, x3, and x4 and take their average to approximate the label at x. So that's how the k nearest algorithm works. First, you define a certain distance, then you compute the distances, then you sort them, and finally you identify the k nearest feature vectors to your test point x. And then the final step is to construct the approximation, but that's just taking the average of all the k nearest neighbors you have identified. So there are two very popular distance functions which are used quite often, and the first one is the Euclidean distance. So let's say you have two input vectors x1 and x2. Both of these are two-dimensional. Okay, then the distance reads as follows: you have x1 and the first component of that minus x2 and the first component of that. You take the difference, square it up, and then you do the same for the second component. So you must have seen this metric quite often. Actually, that's the one you use most often when it comes to Euclidean geometry or doing trigonometry, etc. The second distance is easier than the first one, and that just takes the absolute difference between the two components. So take the first component of x1, the first component of x2, take the absolute difference between the two, and then do the same for the second component. Okay, so these are the two most popular distances which you will see in the literature being used. But as I said before, you have a lot of freedom in defining these distances. You just need to find a function that satisfies these three properties, and that's a valid distance function. And the way you define the distance function would really control the quality of your approximation here. So if your distance function is incorrectly defined, your approximation quality can change because depending upon the definition of the distance function, different k neighborhoods can be identified. Let's take an example where these two different definitions of the distance functions would lead to different neighborhoods. So as before, let us consider a two-dimensional feature space. So we have two dimensions, x1 and x2, and in addition to that, let's place points along a circle. So let's take a circle of radius 1 and assume that this here is the origin of this circle, and the distance is 1. So this point, and the radius is 1. So this point would be 1 comma 0. This point would be 0 comma 1, minus 1 comma 0, and then 0 comma minus 1. So these are the 4 data points that we have, and in addition to those 4 points, we also have 1 over square root 2 and 1 comma square root 2. So this also lies on the circle. So now what we're doing is we're trying to find the 4 nearest neighbors of this point at the origin, and we consider these two metrics. Just for simplicity, I'll call this d1, and the second one I would call d2. So if you compute d1, right, by the definition of the radius, the distance of 0 comma 0 to this point would be 1, and to all the other points it's also 1. Okay, so all these 5 points are valid candidates of the 4 nearest points to the origin. So if you were to now compute the k nearest approximation, you could choose any of these. You could choose 4 points out of any of these 5 points, and you can choose them randomly. But let's look at what happens when d2 is our metric. So when we choose d2 as our metric, all these distances to points which are along the axes, they would remain the same, but the distance to this point would change, and in case of d2, the distance to this point would be square root of 2, right? And you can see that obviously square root of 2, which is approximately 1.4, is greater than all the other distances. Then only these 4 points are the nearest neighbors, and this one and this last point, which is not along the axis, this won't be a valid point. So this won't be considered with the d2 metric. Okay, so this example shows you that depending on the definition of the distance metric, the k nearest points that you identify would change, and this in turn changes the approximation that you have up here. Okay, so that wraps up regression, and next I will be discussing classification. So for classification, the output label is discrete. It could either be 1 or 2 or any value between 1 and c, where c is the number of classes. That's the number of classes you have. And the technique to identify the k nearest neighbor would remain the same. So let's say you have 4 training points in a 2-dimensional feature space, and your test point is this red one. So to identify the 3 nearest neighbors, you would do the same thing. So you would compute the value of the distance function to all these 4 points, and then you would select the 3 points that have the minimum distance. In this case, it would be these 3 points. So these 3 points would be your k nearest neighbors if k is equal to 3. So once you have the neighborhood, the question is, what is the approximation for the ground truth? So what you do is as follows: you just check which label is in majority inside the neighborhood. So let's say this point had label 2, this point also had the label 2, and this point here had the label 1. Then the number of 2's is equal to 2, which is greater than the number of 1's you have. This implies that f of x would be the second class, in this case denoted by 2. So there are 2 steps to doing classification using k nearest neighbors. The first step is finding the neighborhood, which is the same as regression, and the second step is just counting which label is in majority. So you count the majority labels inside the neighborhood. And that's all. So only the second step changes. The first step remains the same as regression. But the next question we will look at is how to choose the value of k. Now, to understand how to choose the value of k, we will look at two extreme cases. The first one is when k is equal to n. That's the number of training points that we have. And in this case, assume you have 4 training points again, and you have a test point which is denoted by a cross. Now, since k is equal to n, which would be 4 for this particular case, then the value or the approximation at this point would just be the average of these 4 values. Now, this approximation wouldn't change even if this test point changes. What I mean is, if I take this test point and move it around, if I place the test point here, then the value of the approximation would be the same, because you're still taking these 4 points as the average. Same would happen if you place the test point here. So the approximation in this case, that's f of x, is independent of x. So this approximation, because it's independent of x, it captures no variation in the dataset at all. So one could expect that even on the training set, which are these blue points, you would make a substantial amount of error. I think this is easier to see with a one-dimensional problem. So let's say you had a one-dimensional feature space denoted by x, and then you had a one-dimensional output space. So you sampled 4 points as before, and your function looks something like this. Okay, so you have the ground truth label here, 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 and here. So what this approximation here would do is it would take the average of all these 4 labels, which would be somewhere along this line. And you can see that even on the training points, you make a substantial amount of error, right? So the error on the training point is quite high. And now let us look at the other extreme where k is equal to 1. So if we take the one-dimensional example again, now if I take a test point and I place it on top of one of these training points, in this case the first one, right? And then I ask for the approximation f of x, then f of x would be nothing but y1, because the first nearest neighbor of this red cross is the first training point itself, so the point on which the testing point is placed, right? So this means that the error I am making on the first training point would be 0, and I could repeat the same process for other points. So I can place my test point on this third point, and then f of x would be y2 or y3. And if I place it here, then f of x would be y4. So this implies that when k is equal to 1, my training error would be 0. So we have two extremes now, right? So when k was equal to n, and that's the maximum number of points that we have, then the training error was high. We were not able to capture any variability even in the training set. And the other extreme is when k is equal to 1, and here the model that we have is extremely versatile, so it's able to capture all the variance in the training points, and as a result we have a 0 training error. Now if you were to plot the training error with k, the plot would look as follows. So let's say we plot on x dimension the value along the x-axis the value of k, and along the y-axis we have the training error. If we were to plot these two quantities, so when k is equal to n, then we have the highest possible training error. Let's call it E max to denote that this is the maximum possible value. And when k is equal to 1, then we have 0 training error. So the training error, and in between these two values, it would decay to the minimum possible value of 0. So it would look something like this. So this is the variation of the training error with k. I'll make a small correction here. This is the error and not just the training error. This is just error, and then we are computing this error on the training set, which results in the training error. So the training error decreases as k decreases. So although the value of the training error at k equal to 1 is 0, we won't be using this value for any of our computations, because at this value of k, we would be overfitting the training data set. And what you would rather do is, in addition to the training set, you would have a validation set. So this validation set will not be used during training. The error at the validation set would look like a U-shaped curve. So initially, the validation error would decrease, and then there would be a point which we could call k optimal, and this is the value that you would need to use for your computations. After this k optimal value, if you decrease k further, then the error would increase again, and this is because you're overfitting on the training set. So in practice, you would be using this optimal value of k to perform your computations.